My name is Matthew McKnight. I'm a technical specialist at Autodesk. I work out of our Melbourne office here in Australia. I might just ask that anyone that has their microphone on, if they could just turn it to mute, that might help a little bit. Excellent. So, what is innovation? Well, there are many academic definitions of innovation, but to put it simply, innovation is the process of having a good idea, validating it, and then monetizing it as fast and as profitably as possible. And this is what most design and manufacturing companies are looking to do with the products that they design and make. Now, as easy as this sounds, there are often obvious challenges associated with it. There are numerous barriers that stop companies from successfully implementing innovation to their organization. First, there's the challenge of time or the lack of it. We all know the feeling of having a great idea for a new product or project that would be disruptive, but we never have time to transform the idea to reality. And this is partly because we're so busy trying to do the day-to-day activities that we have, and this distracts us from the things that are often adding value to our business. Even then, when we do start working on one of those ideas, the challenge quickly shifts to our ability to rapidly test and iterate through a series of ideas, and to find the ones that are good enough to move through the development process, and others we can quickly rule out. And then there's the rapid development of new technologies transforming the way that we design and make things. Whether it's new materials, design techniques, or manufacturing processes, we often overlook these or completely rule them out by exploring some of these. And by exploring some of these opportunities, could this help drive innovation in our companies? Now, I'm lucky enough to visit and talk to numerous manufacturers each year, and the feedback that I gather from them is similar to the results of a recent survey which was conducted by Tech Clarity. This survey found that a lot of industrial machinery manufacturers configure to order or engineer to order. It didn't really matter whether they were a top or average performer. The results were fairly similar. The real difference here lies in how the top performers were able to effectively perform this activity and differentiate themselves from the average performers. Top performers were much more likely to use platform design, modular design, or rules-based design, each offering the benefit of being able to reduce the overall development of a product. Rules-based design, however, stands out from the others because this form of design is much more likely to be used by a top performer than it is by an average performer. Keep this in mind because in a moment I'll show you a rules-based design solution that can help significantly reduce the time it takes to configure or engineer to order a design, freeing you up to focus on other products or projects and helping you to become a more innovative company. Another area we can waste time is simulating our designs. Simulation is fast becoming a much more integral part of the development lifecycle, helping us to make better decisions about our designs and to make those decisions faster. But part of the challenge of using simulation is the way we integrate it into the development lifecycle. A solution that's not an integral part of this process can add additional steps requiring information to be passed between separate design and simulation software. The result often means that users spend considerable time updating simulation setups to reflect the changes of a design. So with this in mind, how can we recover some of the time wasted creating and simulating our designs? Let's take a moment to look at such a workflow. So in this example, we're going to be working with a robotic welding cell, and our customer here has requested for a high-mounted robotic welder. We need to design a brand new structural frame that we know is going to meet our customer needs. We want to make sure that we start inside of Inventor, and we do this is to make sure that all of our data is not only secure, but also managed effectively. Here we can open from Vault, where we'll check out all of the relevant components, and this ensures that no one else is editing the files at the same time. We'll start with one of our customizable iLogic assemblies. This will help us automate the design process and save valuable engineering time. Here, iLogic enables us to explore different design combinations in real time. We can change height, depth, width, and top angle, and even suppress the front braces if we don't need them. Once we've got all of our customer requests in place through the design options we've selected, we can save this new design and check it back into Vault. Now, an alternative way to explore the new design options is to work with the same iLogic form, but use a drawing template. This is a great way to quickly respond to RFQs, and here because drawings are automatically updated in minutes rather than days. We simply input the customer requested options, adjust the updated dimensions. Now we're all done, we can check the design back into Vault. Here, this enables us to then move on to the validation part of the design workflow. Now, because we're using the product design and manufacturing collection, we can use Nastran in CAD right inside of Inventor. Once we get into Nastran in CAD, we'll simply start the setup of our simulation. And since we've got a structure with plate and structural tubing, we can simplify the model down to mid-plane surfaces. This allows for the same accurate results in a fraction of the time. Working from right to left, we'll add some constraints to the bottom of the feet. We'll apply a load where the top surfaces are supporting the robotic welder. And since we're working with surfaces, we need to set our contacts or define our contacts and the relationship they have in the surrounding geometry to ensure that all of our surfaces are in contact with one another. Using our mesh settings, we'll adjust our element size and click Generate Mesh. Using a finer mesh will give a better resolution, and since we're working with surfaces, it'll still run extremely fast. Once our mesh is generated, we can run the simulation, and after our simulation is complete, we can adjust some visibility options to help us understand areas of concern within some of our design. Next, we can animate the results, and keep in mind here the deformation you see is exaggerated to help identify areas of interest. As we take a look, you'll see that von Mises stress is well under the yield of our steel material. You'll also see that the maximum amount of deformation and how much it's actually moving. In this case, it's moving less than 1 millimeter. Now consider what would happen if we add the braces back in and see how much it improves our design. We'll copy the analysis and all of our setup, and we'll add the braces back into the design, making sure that we capture the new surfaces. We'll remesh and rerun our analysis. And then when we look back at the results, you can see that we've cut the displacement in half, as well as reducing the von Mises stress as well. So with this in mind, now that we've validated the design, we can get everything back into Vault and move on to the next step of the design process. So the areas shown in the previous workflow highlight how you can help reduce wasted time. But there are other factors beyond this where we've just shown that you should also consider. Now, the survey that I referred to before, the Tech Clarity Survey, found that engineers waste on an average of 15% of their time managing design data. Some of this is in key areas like sharing information with other departments, finding the right information, managing change, working on the wrong or outdated information, reusing data, and collaborating with engineers in different locations. The worst offenders wasted the equivalent of a day, a week or more, and this is for each engineer in the company. Those who can relate to some of the previous points that I made around finding information and data reuse really need to be asking, what is the value of the time of that time to you and the time that you're actually losing? And like we've said, collaboration is an essential part of the development process. Nearly half of all companies surveyed by Tech Clarity said that collaboration is a significant challenge for them. There are the typical collaboration issues, many of which are internal to a company, issues with sharing data between departments or working on the wrong data. But it doesn't matter whether you're looking internally or externally. Engineering teams experience challenges working together with other departments and with external suppliers and customers. Now, the final area is working with non-native data, and in this instance, we're talking about change outside of the company. Another survey from a few years ago looked at the time engineers spent fixing broken links in their system as a result of design changes. It found that as much as 49% of engineers spent at least 4 hours a week fixing broken geometry. Maybe this is because your customer or supplier is providing files from a design system other than Inventor. They might be in another format, maybe SolidWorks or Creo, or maybe they're in a neutral file format like Step or IGES. Either way, updating designs and downstream processes can be significantly hindered when a file changes, often resulting in significant time updating your designs to reflect the changes. So how can we recover some of the time wasted managing data, collaborating, and working with non-native file formats? So let's take a moment to have a look at such a workflow. Now, one of the easiest ways to free up capacity for more innovations is to manage your data better and make collaboration easy. Here, using Autodesk Vault Professional allows us to track changes, understand what's work in process, what's for review, and ultimately what is released for manufacturing. Another benefit of using Vault is collaborating with shared views. Now, shared views allow you to share designs without giving your data away. Here, you can view in a browser or copy the link to share with both internal and external stakeholders. And the Autodesk viewer then allows you to zoom in, pan, rotate, explode, and measure. You can also add markups and comments. And in this case, we know we need to replace the welder base with an updated model from the vendor. After we've saved all of the markups and comments, all of these are automatically tracked and associated with the assembly. Shared views can also be accessed on a mobile device, and this allows you to collaborate with virtually anyone, anywhere. Now we're going to open the assembly from Vault and check it out. Once we have the file open, we can go to the Collaboration tab and open the Shared Views panel. And inside of this panel, you can see that the comments have migrated through to this, and we can now take action. We'll change our selection priority and open the base. You'll notice that this is a SolidWorks file that has been placed using the AnyCAD technology. This means that when we replace the current file with an updated version from the vendor, our base plate which is associative, will automatically update. Any of our associated documentation will also update it, so the 2D drawings will follow through. So with our 2D and 3D geometry up to date, we can check our assembly back into Vault and move to the next step of our design and manufacturing workflow. So we've already shown numerous ways you can help reduce wasted time in your development process, but let's take a moment to look at a few more. And these are related to the manufacturing workflow. A common waste of time comes from moving data between the design office and the factory floor. Moving designs from our CAD software to a CAM software often requires translation, which results in a broken workflow. As a result, changes to the original design of the CAD software aren't linked to the downstream CAM toolpaths, meaning that time has to be spent importing and then recreating setups and toolpaths, something which may have already been done. It might be that managing the revisions of designs or drawings that often results in the wrong parts being made. Though a design may have changed in the engineering office, how can we be sure that the factory are using the correct version when it comes time to make it? And similarly, nesting of sheet metal parts is often a manual process. At best, it might be done using separate nesting software, but even then, changes to the original design may not flow through to any nests already generated. So how can we recover some of the time wasted translating files between software, managing file versions, and reducing the amount of rework when a change occurs? Again, let's take a brief moment to look at such a workflow. So let's look at how we can better connect design to manufacture with in-canvas CNC and nesting workflows. We'll start by creating an adaptive 3D milling operation for a robotic welder mounting plates. Here we'll select a machining boundary and a top height directly on the model, and this will allow for automatic toolpath updates if your model changes. Next, we'll use 2D adaptive to mill out the inner pockets, and you'll notice that our first operation is still programming in the background. This is one of the key features that allows for simultaneous programming. We'll add a derived operation for a 2D contour and a flat end mill. This will clean up the pocket bottom since we're using a sacrificial plate under the part. We'll also add another finishing toolpath for our inside face. The sloped edges on the back will require a 3D toolpath, but with our milling done, we can start the drilling operations. Now we'll start out with a spot drill, and we can use this select same diameter to quickly select all the holes. We can duplicate the spot drill operation and select the drill size we want. On the height tab, we can adjust the drill bottom height. We can make sure, though in this that we can check the drill through bottom and add a breakthrough depth to ensure a clean exit. And here we'll also adjust the cycle to chip break to keep the chips flowing. Next, we can simulate the toolpath and use the information tab to look at the detailed information about every part of the toolpath. Using both ways adaptive allows us to cut and climb, and conventional, making better use of tool movement and faster roughing times. When our simulation finishes, we get a notification that our part has been changed. And since we're working within HSM, which is inside of Inventor, our toolpaths are associative. All we need to do is select generate toolpaths, and all the previously generated toolpaths automatically update. Now, the next workflow we want to look at is the nesting of sheet metal components. Here we'll start with a quick search in Vault and open with checkout of the assembly that we're looking for. To get our nesting started, we'll click on the top level assembly and select nest. I'll select my customized nesting template and click OK. And any flat patterns in the assembly are automatically added to my nest, and the materials also pulled over. The next step is to click create, where we'll accept all of the defaults and click OK. The nesting utility automatically nests components made with similar material and thickness. It also picks up the quantities of the individual components automatically. We'll click the boundary of the nest we want to work with to zoom in. And now we'll right-click the boundary and create a 3D model so that we can move over to HSM for laser cutting. Here we'll select the CAM tab and set up to get started. We'll set the orientation to the lower left corner of our stock and change the operation to cutting. Now on the stock tab, you'll select from solid in the drop-down and pick the stock body. Next, we'll add a cutting operation with a 2D profile. We'll select the first face and then tick the box for select same plane faces. This will grab all of the components within the stock boundary. Now back over on the tool tab, we'll change the type to laser cutting and click OK. Now we're ready to simulate. Simulating the laser allows us to visualize and evaluate the toolpath and make any adjustments needed prior to sending it to manufacture. Now that we've verified all of our nesting requirements, we can check everything back into the vault. And this associative in-canvas CNC and nesting workflows help reduce design and manufacturing errors and rework. Let's look at what most of us know to be the current design process. Given that nobody has an unlimited number of resources, nor do we have an unlimited amount of time to explore alternate ideas, we've learned to make moderate improvements to the products we bring to market. With limited time, we often select designs which largely resemble the few concepts we are limited in creating. We then, as part of a serial process, evaluate for strength, fatigue, or performance, and again move on to the next step in evaluating manufacturability. Now, this process is linear in nature, serial in its process, and the time available to explore more ideas is limited to that which meets our production schedules. This is where generative design technology from Autodesk is radically different. Generative design provides validated design alternatives by evaluating the problem, strength and performance requirements, and manufacturing processes all in parallel, performing the function of generating geometry based on multiple criteria and freeing the geometry creation burden from the engineer. This enables you to explore a much wider solution domain, expose more information about validated manufacturable options in order to make the most informed decision about what is the best for the business. And not only this, but in comparison to a traditional development workflow, you can potentially save considerable development time by using generative design. Alternatively, it might allow for a much broader investigation of design solutions in a similar amount of time. So traditionally, innovation takes an investment in time and resources, especially in design and engineering, with design, test, design, and test again methodology. But with generative design, you can explore multiple design solutions based on real-world manufacturing constraints and product development requirements. In this example, we want to improve the performance of our robotic welder. Here, we're looking at the end effector and see if we can reduce the weight and overall the complexity of the subassembly. The result is significantly lighter, which gives our robot better performance. We also have a simpler assembly that's faster to assemble and maintain. So let's have a look at this process. With generative design, you define the conditions, not the geometry. We start with what is called preserved geometry. These are the connection points and mating geometry that are required in the final design. Next is the obstacle geometry. This is where you don't want material to go. Think of things like holes and clearance areas. After you've modeled these inside of Fusion 360, you can hit generate, and inside of generative design, under the design space, we simply select the preserved geometry and assign it, and then do the same for obstacle geometry. Next, we'll define and identify the constraints, or where this is being held. In this case, the connection of face to the robot welder. We'll then add the loads or the real-world conditions that our parts need to stand up to, or preserve geometry connection points. Our objective is to minimize mass, and we'll add a safety factor of 7. And this helps give the generative design algorithms some guidance. We'll choose unrestricted and additive manufacturing methods, and then choose our materials with as many as 10 being able to be specified for each study. We'll set the synthesis topology to accurate. This will help give a tighter resolution. Once we generate our study, we can then go through and explore out the outcomes in a couple of different ways. Once we find a study that meets our needs, we can export it to SAT or STL file. In this case, we're going to open up inside of Inventor and drop it into the robotic welder assembly. Now, generative design helps deliver innovative engineering and design solutions without the traditional investment in time and resources. So what you've seen today is an overview of the kinds of workflows that are possible using the product design and manufacturing collection, because everyone involved has access to a complete set of solutions that make up our best inventor. Whether you need the professional grade design and automation tools, the advanced simulation capabilities, the multi-axis CAM workflows, the embedded nesting technology, or factory planning capabilities, all are accessible through a single application and a single subscription. And while individual roles in an organization might use certain technologies, more often than others, everyone is working from and has access to all the information that makes up the complete product definition.